All right, welcome to Physics 106. So we're starting off with Chapter 17, which is a continuation of Chapters 15 and 16 that we did in 105. So this is about wave optics. So it's the wave theory of light. So interference and diffraction. All right, so this is a really long chapter, and you can kind of tell that by all the learning objectives. So we'll use the wave model of light, understand the domain of its applicability, understand how the index of refraction affects light waves in a medium. That means when light goes through glass or water or something like that, as opposed to air. Understand the importance of path length difference in determining the kind of interference, constructive or destructive, that is observed. We did that in Physics 105, either 15 or 16. Calculate the positions and angles of bright and dark fringes and double-slit interference. We'll be talking about this double-slit interference a lot, even when we get in later on when we talk about quantum mechanics. Understanding the diffraction grating in terms of many interfering slits, and be able to predict the positions and angles of the maxima. Use the conditions for constructive and destructive interference in thin films. I promise you there'll be homework problems on this and test questions on this. Understand the inevitable spreading of waves due to diffraction, and then understand how light diffracts through single slits and circular apertures. And, you know, circular apertures, telescopes, microscopes, all sorts of things. Now, let me warn you, there are many, many equations in this chapter, and you have to understand where they come from. So I will be asking you to derive equations. Now, if this were a regular classroom, I would stand here and wait. I would give you like 5 or 10 minutes to do it. Well, we can't, I mean, now, you know, I'm just going to say pause your video, but I promise you, if you just ignore me and don't bother deriving them and just, you know, watch me do it, you're not going to learn a whole lot. And when you get to the test, you're going to be lost. When you get to the problem sets, you're going to be lost. So when I ask you to derive something, please actually do it. All right, we need to review Physics 105. So here we have two identical speakers. What is the only difference about the sound wave from each speaker that arrives at the listener? Remember, they're identical speakers. So what's the only difference between the sound wave from speaker 1 and the sound wave from speaker 2? Well, it's sort of obvious, right? It's the distance that the wave travels. Speaker 1, the wave only travels this distance. Speaker 2 travels this distance. Speaker 1, the wave travels this distance. Here, speaker 2 travels that distance. So there's we call it a path length difference. This is a slide from 105. You've seen it before. So there's a path length difference. And as we discussed in 105, if you have identical speakers, the path length difference has something to do with if you're going to get constructive interference or destructive interference. So again, just reviewing that. All right, so if the path length difference is one wavelength, here's a picture, okay? So here's the path length difference, right? This is the difference in path lengths, this distance right here. And you can see here that the path length difference is one wavelength. Well, look what happens. So these two waves are in phase, right? The speakers are one wavelength apart. The crests are aligned. I would say the maxes are aligned, the mins are aligned. So what kind of interference are we going to get here? It's constructive, right? It's a perfect example of constructive interference. And you know, that would happen if the wavelength, if the path length difference is 2 wavelengths, 3 wavelengths, any integer times a wavelength. On the other hand, we call that constructive interference in phase. So we say that the waves are in phase, because you get this nice constructive interference. On the other hand, let's say that the speakers are a half a wavelength apart. Well, look what happens. So, right, this is just a half a wavelength here. This distance is a half a wavelength. And so here, this is up, this is down. What kind of interference are you going to get? Destructive, right? And so what's the sound at this point? Zero, because it's perfectly destructive interference. So we call that out of phase. And this, all right, so I'm just repeating myself, right? Oh, let me get back. So you'd have this destructive interference if this were half a wavelength, 3 halves, 5 halves, 7 halves, on and on and on. So we can generalize. We can say if we want constructive interference, the path difference, I'll just call it delta D, has to equal 1 wavelength, or 0, right? 0 wavelengths, 1 wavelength, 2 wavelengths. We can just say that nicely like this, where m is an index, right? Integers. Now, for destructive, the path length difference is a half a wavelengths, 3 halves, 5 halves, da da da. And you can write that nicely like this, right? If m is 0, you just got a half a wavelength. If m is 1, you get 1 1/2, which is 3 halves. If m is 2, you get 2 1/2, which is 5 halves, on and on and on. All right, so you should be familiar with that from Physics 105. And we've seen this before too, right? So what is the path length difference? So pause your videos and figure it out. Okay, so this one travels all the way to there and back. This one just like that, right? So this one travels 150 nanometers this way and then 150 nanometers that way. So the path length difference is 300 nanometers, right? And one last, again, you've seen this before too. 2 identical loudspeakers are placed 1.5 meters apart. Both speakers emit identical 343 hertz waves. That's a nice number, right? Because the speed is 343, and you use this equation. Don't forget this equation is super important for waves. What kind of interference you have at point C? So pause your videos and figure it out. All right, so we're given that this is 2 meters. This is a 1.5 meter, so this has to be 2.5 meters, just Pythagorean theorem. So what's the path length difference? Well, this travels 2 meters, this travels a half a meter, so the path length difference is a half a meter. All right, what's so great about that? All right, so path length difference, I call it delta D or whatever you want, it's a half a meter. Well, we got to compare that to the wavelength, right? Okay, so we know that V equals F lambda, so we want wavelength. So lambda equals V over F. This is a nice problem because it says V is 343 meters per second, and frequency is 343 hertz, which is the inverse second. So the wavelength is 1 meter. Okay, if the wavelength is 1 meter and the path difference is a half a meter, that's destructive interference, right? That's destructive interference. So there you go. All right. Okay, so that's your review. All right, that's your review. Now, if this were a normal classroom, I would do some demonstrations, but we can't, so I'm sorry. All right, so pretend I had a here's a laser pointer. Hey, pretend I had a laser pointer. And, you're outside, especially at night, and you shine your laser pointer, to see, to kind of indicate where a star is or a constellation or whatever you like, right? What does it look like? The laser pointer goes in a straight line, right? Straight line, okay? And so we say that the ray of light, it acts like many bullets, right? They just go straight, okay? So that's like the ray model or the particle model. Or let's call it the ray model of light. All right, now on the other hand, let's pretend this is a super narrow slit. I mean narrow, like super, super narrow. And you shine a laser at it. And, if light were just made out of bullets, you would just see one bright line on the screen, right? Because you would just say, if light's bullets, it just goes through the slit, and you just got one bright line. But what happens, look what happens. The light spreads. Not only does it spread, though, you get dark light, dark light, dark light, dark light, interference pattern, Whoa, okay. So what do you know? Okay, so that's called diffraction. We'll talk about that more in gory detail. Now, where else do you see something like this? Some kind of you have a wave going through opening and it spreads and you see some kind of a pattern. Where else do you see that? With water, right? So here's a wave of water and here's a narrow slit and you can see that it's sort of some kind of a bending, you know? So that indicates that light acts like a wave, right? Like a wave. There's a third model, which we'll talk about near the end of the semester. It's called the quantum model. In the quantum model, light acts like a wave and a particle, which is kind of hard to imagine, but we'll get there, all right? And the quantum model is the basis for all of electronics, computers, cell phones, I mean, you name it, the entire high-tech world. So it's very important. Again, we'll discuss it later. All right, so like I said, this chapter is about the wave model of light. All right. Well, first of all, hold it. What's light? You know, what's light? It's a self-propagating wave, and it doesn't require any kind of a medium. It doesn't require a material medium. What are you talking about? Well, you know, if you have a rope wave, which we talked about in 105, what's the medium? Rope, you know. If you have a sound wave, what's the medium? Air. If you have an earthquake wave, what's the medium? Earth. If you have a water wave, what's the medium? Water. So, you know, we've only talked, these are called mechanical waves, because there's always something, you know, physical, right? There's also always something physical, material, that moves, you know. Air for sound waves and, you know, the rope and earthquake and all that. Well, a light wave can travel through a vacuum. I mean, think about it. What's between the sun and the Earth's upper atmosphere? It's basically a vacuum, you know. So there's nothing material that's moving. That's kind of weird. But we'll talk about it later. Don't worry about it. The speed of light in a vacuum, you're going to see this a lot in Physics 106. So they use lowercase c to denote the speed of light in a vacuum. 3 times 10 to the 8th meters per second. It's really fast. 186,000 miles a second. 671 million miles an hour. Okay, it's really fast. Now, we learned this equation before, right? That's true for every wave. For light, since the speed of light is lowercase c, we have c equals f lambda, which is, again, you know, it's constant, right? 3 times 10 to the 8th meters per second. So this is stuck. 3 times 10 to the 8th meters per second. It doesn't vary. Constant. But what does it say about f and lambda? Well, they can be anything as long as the product equals 3 times 10 to the 8th meters per second. Okay? Now you say, so what? Well, if you study astronomy, that's incredibly important. And here's why. So this is called the electromagnetic spectrum. Think of it as the light spectrum, all right? So this shows you the different types of light. And so there's gamma rays, X-rays, ultraviolet, visible, infrared, microwaves, radio. Now look at, think of this entire spectrum. How much of this entire spectrum is visible light? Just this tiny little region, right? Just this tiny, tiny little region. So think about it. You know, if you're an astronomer like 50 years ago or something like that, or maybe, I don't know, 60 or something, and all you had is a visible light, you know, ordinary telescope, well, how much of the entire light spectrum are you seeing? You're seeing this tiny little bit. You're missing all of this. You're missing all of that. And this doesn't stop here, you know, it just keeps going. This keeps going. So, I mean, all you're seeing is a little tiny fraction. Well, that's no good. Oh, by the way, look at, so this is like, look at the range of different types of light. So look at the wavelength. So gamma rays that are used to kill cancer cells, super short wavelength, 10 to the minus 12. Visible light, what's the wavelength of visible light? 10 to the minus 6. You know, it's the size of bacteria. Visible light is super, super tiny. I mean, wavelength is super, super tiny. And here you can have 100, 1,000 more, you know? So it's incredible the different sizes. The frequencies, okay, this is like 10 to the 20. That means here's like 10 to the 14th or something, 10 to the 6th, you know? Look at the energies. 10 to the 6th, that's why it's used to kill cancer cells. Visible light, like 10, or 1, you know, nothing. and then here like 10 to the minus 8, which is super small. So anyway, now let's talk about astronomy. Why is this important in astronomy? Okay, so here is a star map of a certain constellation, Orion, and here is what you see in the night sky. So, you look at that and say, oh, that's nice, very nice, right? See the, okay. But then, so this is V for visible light, but then look at what it looks like in ultraviolet. So if you're used to seeing this, and then all of a sudden somebody shows you that, whoa, what is going on here? Like, what's going on? Why is it so incredibly bright? Look at this. This is infrared. You got to explain all that, right? There's a lot going on here that you'd never imagine if you just look at this. So, there's been a lot of discoveries because people have figured out how to make infrared cameras and satellites and microwave and radio telescopes and UV and X-ray and gamma. So people are learning tons of things that they never even dreamed of before, just because they're able to see more, right? That's incredible. They're able to see more. So it's very, very important. Okay, so hold on. This here is the speed of light in a vacuum. Now, oftentimes light goes through something else, like water or glass or something like that. And when light goes through something that's not a vacuum, it slows down, okay? So it doesn't go this speed, it goes slower. So there's a nice way to categorize that, and it's called using this N. So N is called the index of refraction. We're going to use it a lot. Well, we are, okay? So N is the speed of light in a vacuum, which is C, divided by the speed of light in the medium, water or glass or whatever. And remember, this is less than C, and so this fraction, this index of refraction, this is always greater than 1, right? Because V is less than C, so it has to be greater than 1. Okay, so we'll use that a lot. Now, so let's say you shine some light at a piece of glass or something like that. So here, the speed of the speed is the speed of light. Then here, it's some medium, and here's another medium. Now, it's an experimental fact that the frequency of the light never changes. Okay, the frequency doesn't change. So this is constant. Now, if the speed slows down, that means that the wavelength has to get smaller, right? Because this doesn't change, And you can see that, all right? So, here's a certain remember, this is the wavelength. So here's a certain wavelength. And what happens here? The wavelength shrinks. Okay? So there you go. All right? So faster wave speed, longer wavelength, slower wave speed, shorter wavelength. And we'll use that. We're going to use all this stuff, believe me. All right? And so let's look at that for a minute. So we have velocity equals lambda f. So lambda equals velocity over f, right? But again, look at, so we have n equals c over v. We can solve for v. So v equals c over n, right? So let's substitute for v. So we have c over nf, right? But we also can solve for lambda here, right? So lambda equals c over f. So here's, right? So that's just lambda over n. So this is, I should have said this is lambda medium. Lambda medium equals v over f. That should be obvious, right? Because I have a v, I don't have a c. So then this is lambda vacuum. All right? So there's an equation. Lambda medium equals lambda vacuum divided by n, or n medium if you want to put it there. It doesn't really matter. So we'll use this equation a lot too. All right? So lambda medium, material, whatever you want to call it, equals lambda vacuum divided by the index of refraction of the material. We're going to use that a lot. So anyway. All right. Now, we'll talk about something called the Young's double-slit experiment. super crucial for the wave theory of light, super crucial for quantum mechanics, which is the physics of tiny things like atoms and things smaller than atoms that we'll talk about later on. So boy, you're going to hear this double slit on and on and on and on and on. So it's easy to do nowadays. It wasn't easy to do when Young did it in the 1800s. So basically, if I were in my regular room, I would have a piece of glass with a dark piece of paper in it, and then I'd have two super, super tiny slits separated by, I don't know, like a 32nd of a centimeter, I mean, just super, really, really close, right? So there's a little slit. I mean, there's two slits really close to one another. So I would hold that up, and I would take a laser pointer and shine it, and you just look on the wall. Now let's kind of go through this. So here, let's say that's the wall, and here's a thing with two slits, right? Two slits, and let's say here's the light. Now, if light were made out of bullets, you know, light would just go through a slit, make a bright spot here. This light beam would go through this slit, make a bright spot there, right? That's the part. I mean, that's like the ray model. But in fact, when you actually do the experiment, you get that. And this goes, you know, on here and on in here. And so you say, whoa, that's not a light, that's not the ray model, that's the wave model, okay? Because this is an interference pattern. So Thomas Young, he did this, no, let me give you a little history, sorry. So Isaac Newton thought that light was made up of particles. So he was like a ray model kind of guy, right? And the reason is because they didn't have really the equipment to really see any of the wave phenomena until Young came around and figured out how to show it. So Young, he had a lot of courage because think about it, Newton was the most famous scientist alive at the time. He said light's made out of particles. And then Young said, nope, light's made up of waves. And he figured out how to do the experiment without a laser. You know, they didn't have lasers back then. And he showed for sure that light created an interference pattern when it went through the double slits. So therefore, light's a wave. So Newton was wrong, you know, what do you know? So here's kind of a nice little picture too. So there's the light source, slit 1, slit 2. Here's the screen. That's what you see in the screen, this interference pattern. This is super easy to explain. I think we already did it. I don't remember. All right, super easy to explain. All right, so the blue, these are the wave crests, or what I always call the max, right? The maxes from S1, and they're spaced a wavelength apart, the blue ones. The red ones are the wave crests, or the maxes from S2. And again, they're spaced a wavelength apart, okay? So let's pick this place right here. Let's look at this line right here. So here you see blue max, you have red max, so you have constructive interference, right? Okay, here, blue max, red max, constructive interference. So everywhere along, see here, you're just going to have these maxes, or mins, right? You know, but right, you can have constructive interference, right, basically, right? Constructive interference. But let's look at this line. So let's look at this point. That's a max from blue, but what is it from the red? It's in the middle of the maxes, so it's a min. So I have a max blue, min red. So what do you get? Destructive interference. So go along anywhere along this line, and it's always going to be destructive interference. So that's why on the screen, you know, you're going to see constructive interference, destructive, constructive, destructive, constructive, destructive. And then you see this on the screen, right? So you see bright, dark, bright, dark. Okay, interference pattern. That's all it is, interference pattern. So this proves, you know, that light acts like a wave. Okay? Notice I'm being careful with my words. I'm saying light acts like a wave. I'm not saying light is a wave. I'm saying light acts like a wave. You'll understand that when we get to quantum mechanics. Well, you should understand already. I mean, well, you'll understand it later, but just remember that light acts like a wave. So what we want to do is we want to determine the positions of these maxes and mins. We want to use the laws of physics, use mathematics, and figure out where those are. And if our predictions agree with data, we feel good about it, right? We're right. Okay, that's physics, right? If your predictions agree with the data, you're right. Okay, so yeah, that's what we want to do, figure out the positions of these maxes and mins. Now, this is actually incredibly complicated, but we're not going to make it complicated. We're going to make it reasonable. So we're going to use an approximation, which is a very, very good approximation. So what we're going to assume is that the distance between the slits and the screen or the wall, this L, is this distance is super much larger or longer than the distance between the slits. I mean, they just make this look big to make it, you know, to make it the picture easy to understand. But typically, I mean, the distance between the two slits is, I don't know, like, you know, I don't know, like 1/100 of an inch or 1/100 of a centimeter, who knows? I mean, tiny, you know? So, all right, so it doesn't look this way on this slide, I agree, but in the real world, this length, this means super greater than, right? Tons greater than, much greater than. So L is tons bigger than this distance, all right? Now, think about it. If this distance is like almost nothing, then what does it look like for these lines, for these rays? Basically, they're parallel, right? And so that's the approximation. And this is going to save us a lot of trouble, believe me, a lot of math. We're going to assume that because this is so much smaller than this, we're going to assume that these two rays are parallel. It's a good assumption, right? Parallel. Okay, now is the time that you need to get a piece of paper and a pencil, and you need to do the derivations that I ask you to do, all right? And just trust me, you need to know how to do this, okay? If we were in class, we'd have you work in groups, but we can't do that now, so whatever. All right, so here we go. All right, so look at this slide, and remember, we're saying that these are parallel. So what's the path difference? What's the path difference between this guy and this guy? So look at that, stare at it. Well, would you agree this is the path difference, right? And remember, these guys are parallel. So we're saying that, you know, this distance is the same as this distance. So this is the path difference, okay? That's the path difference. All right, now, here's the crucial thought. You do it yourself. What is the, okay, we're going to call it delta R. You know, sometimes call it delta D, sometimes delta R, whatever. What is the path length difference, delta R, in terms of D, this is the distance between the two slits, and this angle theta, right? So you figure it out, just trigonometry. What is delta R in terms of D and theta? So you figure that out, please. Okay, I hope everybody got that, right? Because, you know, just look at that. What is the sine of theta? Well, it's opposite over hypotenuse. I'm sorry, hypotenuse. Opposite over hypotenuse, right? So sine theta is opposite over hypotenuse. Opposite is this delta R. That's a delta. And the hypotenuse is D. So therefore, just multiply. So delta R equals D sine theta. Okay, so that's the path length difference. Delta R is D sine theta. All right, wonderful. Okay, so if we want constructive interference, what did we just learn a few minutes ago, and what did you learn in Physics 105? What does the path length difference have to be for a constructive interference? Well, one wavelength, two wavelengths, three wavelengths, right? So for constructive interference, that's what it is. So the path length difference is one wavelength, two wavelengths, on and on and on. All right? So that's fine. All right, so what's the next question? What's the condition for destructive? Well, like you learned a few minutes ago in 105, the path length difference has to be a half a wavelength, 3 halves, 5 halves, so forth and on, so forth and so on. So this is a nice way to write it, right? So the path length difference is m plus a half lambda, which is 1 half and 3 halves and 5 halves and on, so forth and so on. Okay? All right, now, what did I say we were going to do? Find the positions of these maxes and mins. Well, let's do it, you know? Okay. When we did oscillations last chapter, we learned a small angle approximation. Remember that? We said sine theta is approximately equal to theta for small theta. All right, so that was called a small angle approximation. Well, that's not the only one. I mean, there's other ones. So we're going to learn a different one now, which we'll use when it's appropriate. So another small angle approximation. So what's the definition of tangent? So tangent theta equals sine theta over cos theta. Okay, now, what's cosine of 0? 1. What's cosine of a super small angle? 1. Okay, so for small angles, this is just sine theta over 1, which is sine theta, right? Okay, so this is another small angle approximation. All right, so for small theta, tangent theta is equal to sine theta. I mean, this is just true, right? But for the small angle, we're saying that cosine theta is equal to 1. So that's the small angle business. All right, so we'll use that once in a while, like now. All right? So, oh, brother. So everybody, please look at this diagram. Use this small angle approximation, and figure out what is Ym. So what is Ym in terms of m, L, lambda, and d? And you're going to use, okay, so figure that out. So pause your videos and figure it out. You have to be able to do this. All right. And you're going to use the equation we just derived a minute ago. You know, you're going to use this. Right? You'll use. All right, so figure out that constructive interference. All right, let's go through it. So, look, we know L, right? We always know the distance between the slits and the screen. I mean, we set it up, right? So we always know L, you know. We want to know Ym. We're going to know the angle. So if we know, okay, here's the angle, right? So what trig function relates the opposite to the adjacent? Tangent. Okay, so we know that tangent theta equals opposite Ym over adjacent L. So therefore Ym equals L tan theta. But what do we learn about tangent theta for small angles? I mean, this is just, it doesn't look like it's small here, but again, just remember, this is, you know, this screen is at the PCC or something like that, right? This is, L is really big. Okay, so tangent theta is sine theta. So we have L sine theta. Okay, now, wait a second. We already figured this out, right? For constructive interference, we already know that d sine theta equals m lambda, right? So let's substitute for sine theta. So sine theta is just m lambda over d. So let's plug it in. So we have L times m lambda over d. And of course, remember, m's the index, so I also want to bring it out in front. So that's going to be m L lambda over d. And again, m is, 1, 2, 3, da, 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 da. All right, so that's it. Okay, so Ym equals m, the index, times L lambda over d. And you have to know how to do that. Right, next one I want you to do. So now do the same thing, but find it for destructive interference. And of course, what are you going to use? You're going to use this one, right? So, all right, so pause your video and do it. All right, let's do it. Okay, so it's basically, I mean, it's very similar, right? So this is still true, this is still true, still small angle, so we get L sine theta. But now the difference is you have to use a destructive interference equation. So that says that d sine theta m equals m plus a half lambda. So therefore, sine theta equals m plus a half lambda over d. So you just substitute it. So you're going to get m plus a half lambda times L over d. Ah! All right. So there it is, right? M plus a half lambda L divided by d. Okay? All right, now, next question. So what's the distance from, say, here to here, or here to here? So in other words, what's delta y from max to max, or min to min? So use these equations that you figured out and figure it out. So pause your video and please figure that out. Okay, let's do it. So let's do the max, all right? So we know that. Oh, wait, so we know Ym equals m L lambda over d, all right? So let's put, all right, so that means that Ym plus 1, right, the next one, equals m plus 1 L lambda over d. So just subtract, right? Subtract. So this to this is a max to a max, right? What's it going to be? So Ym plus 1 minus Ym is just going to be L lambda over d. Okay, so that means that this distance from a min to a min or a max to a max is just L lambda over d. So we're going to use all of these, all right? I'm not just wasting your time. Okay, now, guess what? All of these results that we figured out exactly agree with the data, completely agree with the data. So, of course, that gives you confidence that the wave theory of light is correct, right? And, you know, in the real world, it's very simple to measure, you know, L and this distance, D, and the angle. And so, you know, if you can measure L, D, and delta y, or, you know, yeah, if you can measure the y's and the l's and the d's and you know the m's, you can actually calculate the wavelength of light. And that's incredible. Remember what I said the wavelength of light was, like the size of a bacterium or something like that? So you can measure the wavelengths of light, which is amazing, right? Experimentally determine those, which is amazing because they're so incredibly small. All right, let's quit.